I'll be presenting some work on label transformations on Procrustean graphs. And this is joint work with a couple of students, Shervin Ghasemlou and Fatima Zaberafar, neither of whom could be here today, and also with Dylan Shell, who can be here today. Just as an overview of the kinds of problems we'd like to think about, we might imagine that we are given some specification of a robot's capabilities, so some information about what kinds of actuators and what kinds of sensors are available to our robot, and a specific task we'd like that robot to solve. The basic question that motivates the work I'm describing today is the question of what kinds of changes, or perhaps more directly, what kinds of degradations to the robot's capabilities will make the robot's ability to solve that task impossible. Right? So this is actually an extension of some work that some of you may have seen at RSS this past summer. We've got a little farther, and I've got some new results to present to you. So just to give some idea of what we're talking about here, we might imagine, for example, some task we'd like to solve with a range sensor. And as theoreticians, we might imagine some idealized, perfect range sensor with infinite range and infinite resolution. And of course, none of us have such a sensor in our labs, right? We have things more like the SICK or Kuyo lasers that have some limitations, right? So we might imagine if we form a plan based on some kind of idealized model for what a range sensor might look like, then a very important question would be, can we actually execute that thing on the actual nugget of hardware that's available in my lab, right? And of course, we could ask similar kinds of questions for transitions from idealized to realistic models of actuation as well. So one natural question, of course, is who cares, right? Why are we so interested in thinking about these kinds of degradations? Well, I'll mention at least two reasons why we are interested in such things. One is just to make an attempt to get across that chasm that exists sometimes between pure theoretical results and practical ones, right? So I'd like to make some progress toward that, but also I at least have a long-standing interest in understanding something about the weakest robots that are capable of solving particular kinds of tasks, right? So if we can understand something about just how far we can degrade a particular idealized model and still be able to solve a problem, then that gives us some insight on what's really required to solve this sort of problem. Okay, so that's where we're going. The basic tool we introduce in the paper to have a go at answering these kinds of questions is called a Procrustean graph. The basic idea is that we want to form discrete time transition systems. And we model both actions and observations. So in all the figures in the talk, you'll see squares indicating action nodes and circles indicating observation nodes, right? So we're imagining a robot that's interacting with its environment. The robot chooses things to do, and we call those things actions. And it's got some kind of sensor capability that tells it what's going on in the world. We call those things observations, and there's a back and forth between the robot choosing actions to execute and the environment giving some responses about how the robot's position in the world is evolving. One thing I'd like to point out here that, in a sense, is part of the interesting part about these graphs is that we allow non-determinism in places that I never imagined that we would see non-determinism before, right? So, for example, you'll notice that in these Procrustean graphs, we allow multiple starting states, right? So we don't necessarily prescribe one particular place for any particular execution to begin. We also allow non-determinism in the transitions, right? So those of you that have studied theory of formal languages or automata theory may recognize this as a construction somewhat similar to what shows up in when we define non-deterministic finite automata, right? One key difference here is that we are assuming that missing edges here are or encoding some kind of information about what actually can happen in the world, right? So in the typical model, in a non-deterministic finite automaton, a missing edge would indicate just a failed execution, and we continue with the others. Here, we're sort of promising that those missing edges cannot occur, right? So here's an example of what it might look like in something sort of recognizable. So you might imagine a robot driving around a pentagonal building looking for its charger, right? And we have actions here. U1 indicates to continue to follow the wall. U2 indicates the action of stopping to charge oneself, right? So we can model these sorts of interactions between robot and environment using these kinds of graphs. Now, I suspect that many of you are thinking, well, this looks familiar. And indeed, part of the reason we are interested in this kind of formal construct is that it generalizes a number of different kinds of formal objects that have been used in a lot of different contexts elsewhere. So you heard mentioned earlier in the session about combinatorial filters. Some of you may have seen universal plans that attempt to specify what the robot should do in any location it shows up in. There's this long line of work on sensorless manipulation and all these kinds of things. And even more recently, Erdmann's work on non-deterministic graphs. All these kinds of objects can be written, sometimes with a little adaptation, but all of these can be written as these p-graphs, right? And so part of what we are interested in doing here is attempting to understand them all under the same umbrella, to get them into a format where we can treat them as one structure that can be manipulated and reasoned about, and questions asked upon it in ways that aren't specific to those individual instantiations, right? Now, one thing that I think is very interesting about these kinds of approaches is that in all of these cases, we can at least think about the interaction between the robot and the environment as a language. Right? So there's actions and observations alternating, and the set of all of those action, observation, executions that can happen, we can think of that as a formal language, right? So one way to understand the role of these p-graphs is as a structured, easily representable, easily manipulable form for these kinds of things. Rather than the just languages in general, which in some cases, as you likely know, some of them are easily represented. Others are a lot more challenging to get into our computers, right? So in that context, we can then think about these p-graphs as a data structure on which we can apply various operations. So some operations that perhaps preserve the language while changing the presentation, other operations that may mutate the language by changing the presentation, right? So in that light, then we can start to think about plans and planning problems, right? One thing that at least surprised me as we discovered the right way to sort of write these things down, in this formalism, plans and planning problems are the same thing, right? In both cases, we write down a p-graph and identify a certain set of states that are the last places that things should end, right? So to define a planning problem, I need to give you a p-graph along with a goal region. To define a plan, I need to give you a p-graph along with a termination region, right? And then we can define the notion of a plan solving a planning problem in sort of a natural way, right? If every joint execution on those two graphs has finite length and either reaches the goal and the termination region, or is a prefix of something that eventually does, right? So the details of this were well, to my opinion, surprisingly difficult to nail down just exactly right. But one important idea, I think, here is that there's this duality between the planning problems and the plans, right? We might just as well ask the environment to form a plan to guide a robot toward its goal, right? So one other class of plans that was of particular interest to us are a class of plans that we called homomorphic plans, or more specifically, homomorphic solutions. The idea of a homomorphic solution is that every state in our plan graph is responsible for or corresponds in a precisely defined sense to one specific state in the planning problem, right? So this seems like a sort of natural thing, but we had to remind ourselves quite a few times that not all plans are homomorphic plans, right? So here's an example. On the left, you see a planning problem based on the simple example we saw before, where the robot's job is to navigate the room and recharge itself, right? So it's very natural to think about a plan that tells the robot to travel around until you reach the charging station and stop there, right? And that is, of course, what one might do. But on the right, you can see another plan that does this in a rather surprising way, specifically by indeed taking several laps around the environment until the charging state in the planning problem and the action corresponding to going to the charging state both occur at the same time, right? So if those two cycle lengths are relatively prime, then you can potentially get very, very long execution before you reach the planning problem, right? So not all solutions are homomorphic, but we actually prove in the paper that if a solution exists, then a homomorphic solution exists, right? That there's this wild and woolly universe of very, very strange plans, but in a meaningful sense, as I'll discuss in a moment. The homomorphic ones are the ones that are of interest. Then finally, very quickly, we can come around to the question of these label maps, right? I promised we'd have something to say about how the robot's capabilities would change. So we can think about maps that rewrite the labels. And the question we want to ask is, what impact do we get on our ability to solve a particular planning problem by applying these kinds of maps? Right, so we can ask for a given class of plans, right? Homomorphic plans, or all plans, or any other kind of constrained subset of all possible plans. Is the map destructive on that set, right? Does applying that map to our p-graph impact or impair the robot's ability to solve that problem, right? And so we can define the notion of destructiveness of a map on a set of plans, and we sort of get three cases, right? One possibility in which that the map doesn't destroy any of our plans, another in which it destroys all of them, and then a third case where some plans are destroyed and some are not. And the main result that I'll mention here is that if a map is destructive on the set of all homomorphic plans, then it's destructive on the set of all plans, right? And this is this gives us some sense that that the set of homomorphic plans is giving us the kernel, that it's conveying the interesting set of plans. I'm out of time here, but just very quickly, let me show you our dirty laundry. I mentioned this chasm between theory and practice, and I would say the biggest weakness is that. Well, I like to think we've got a little further, but we've got a long way to go. In particular, there are many facets of how things work in the real world of robotics that that would be a challenge to model in this in the current state of things. We'd like to get a little closer. And with that, I'll stop. I'm a little late already, and I'll answer questions.
Okay, questions? Yeah, in the back.
So,
okay.
have you tried taking a look at any of the related work from hybrid systems in terms of bi-simulation relations or things like that, and how that might help address this notion of homomorphic plans or anything like that? If you're familiar with any of that work at all?
Yes, right. So the interesting thing here is that I think the two directions of research are essentially orthogonal, right? So at least my understanding of hybrid systems is that, that there's this very close attention paid to the underlying continuous dynamics here, right? And we can model these kinds of systems that I'm showing you here in that same way. We can write some differential equations and attach them in various places. But we're setting that aside here, right? We're thinking more directly about things at the discrete level, right? And I think a lot of the results end up in the same place, right? In in our explorations, there are various questions you might like to ask about these p-graphs that are similar to questions that are asked about hybrid systems. And in both cases, you could summarize those results by saying all the interesting things you might like to do are NP-hard, right? I think to really go forward, we have to ask the question, how do we get around that, right? How do we actually answer questions that are of interest in a way that works in some practical way?
So my response to that would be, in many cases, the use of bisimulation relations is an attempt to take those continuous dynamics and turn them into a discrete graph that you can then try and apply this sort of logic to. That's frequently how they can be used. And so it builds these discrete transition systems, and then you can try and reason using bisimulation relations there. Just trying to fit that into this framework, in some sense, it might allow you to take these systems where, these practical systems that the practitioners care about, and turn them into something that maybe is a p-graph or some way to convert them between the two.
Yes, I agree. So one critical question here, of course, is where do p-graphs come from, right? And I agree with you completely that these sort of hybrid kinds of models may be a very nice way to bridge at least a little further along that gap that we're trying to get across.
So yeah, let me follow up. It turns out that bisimulation relations, you're correct. So they're meant to handle discrete transition systems, which kind of are abstractions of the continuous dynamics, but they have their origins in computer science. And there's actually a categorical theory framework for simulation relations, bisimulation relations, that operates on fairly general categories. So what might be interesting is see if you have a generalization in that framework, and hence could do bisimulation related to these other constructions in this sort of more general categorical framework.
That would be awesome.
I can do that.
Yeah, let's. Let's talk about it more.
Yeah. Question.
So, just a quick question: is there the same way that in non-deterministic finite automata there's a notion of minimality? Is there kind of a notion of minimality at play when you're talking about homomorphic plans versus p-graphs?
Yes, we've got a paper about that coming out in the IEEE Transactions on Automation Science and Engineering any day now, right? So I think time is short, so maybe I'll stop there. But yes, let me summarize. Finding, let's say, the smallest plan that solves a problem, NP-hard.
Is it equivalent to NFA minimization?
Not quite equivalent, but it's the same kind of flavor.
Any other questions from the audience? Cool. Can I still ask you a question? Okay, you have many examples in the paper in which you show that many of the graphs you can see in applications already are actually p-graphs, right? And even the planning graphs that you use, like in the Erdmann, Mason, and Goldberg framework. So would any algorithm that you can write in pseudocode be translatable into a p-graph? Like with conditions being equal to observations and actions being equal to assignments?
Yeah, so the standard of any algorithm is...
so any paper and wafer?
Let me just go far out on limb here and say, yes, we are superseding every paper ever published in wafer. No, I think the key ingredient that is necessary as we're writing things now, that is of course absent in much of the work that happens in this community, is the continuous time piece, right? And as we're approaching things now, there's the discrete time nature of things is baked in at the very beginning, right? Even if we can avoid drawing specific graphs and think only about the languages, and languages are sets of sequences of discrete symbols, right? So so that limit is pretty clear. Whether there are other exceptions to it, certainly yes, but okay. That's the most obvious one.
So does your stuntman in the picture make it to the end, or?
Well,
doesn't look that way.
I'll leave you to draw your own conclusions.
It's continuous time.
Oh yeah. Okay, thank you. Thanks. Let's thank the speaker once again.